On ktalk.co.za,
on the app,
on DSTV channel 885,
and across the city on 567 AM.
Join the conversation.
This is Cape Talk.
This is Cape Talk.
It's just after 9:30 on a Friday, which means it's time for The Naked Scientist. Dr. Chris Smith answers your science and natural history related questions. Dr. Chris Smith, hope you're enjoying your Friday morning. I hope you're enjoying your long Jubilee weekend. You should, in all intents and purposes, take the day off today, shouldn't you?
Well, that's true. But then I thought, why not come and talk to my friends in South Africa? And actually, there will have been a big beacon lighting ceremony in South Africa, just like there was I was at last night, in cities, towns, villages, and the main capitals across Commonwealth countries around the world. There was a big beacon lighting ceremony in the sort of early evening of last night. It was absolutely brilliant, actually. And as the guy who announced it, as this beacon was lit, said, never in our lifetimes will this ever happen again. And I paused for a moment because you always worry when people use the never or always word, because I was drilled into me when I was a medical student. Questions that have always or never in them are almost always wrong. Well, actually, I thought about it and thought, no, he's absolutely right. We never will see the like of this again in our lifetime. So it's a very poignant moment. And it was also very poignant to watch the RAF Typhoons fly over, producing a formation of the number 70 as they flew over London. I've never seen such a brilliant display of aerobatics. What an amazing bit of skill those pilots have. But no, it's really, really lovely, actually. And the weather's good too, which, I mean, it all comes down to that, doesn't it? Normally, you can rely on the British to have rubbish weather. And on this occasion, it has bucked the trend.
I enjoy a bit of pageantry. I can appreciate some pomp. We all like a little pomp now and then. But the aerodynamics of flying jets ties in very nicely to this first question. I know in the UK as well in South Africa and around the world, people are battling with the high price of fuel. So here's a question here from that we wanted to tackle first, and it says, "Hi Chris, fuel prices have gone up the world over and hit a record high this week in South Africa. We know that drag can be reduced by slipstreaming, like those jets and birds who fly in beautiful V formation. Some people ride dangerously close to the vehicle in front of them in an effort to save fuel. But of course, the danger is a rear end collision." Two questions. How far back can one still get the benefits of the vehicle in front disrupting the air, or are the effects lost when following the second gap rule? I don't know what the second gap rule is. And second question, would there be any benefit to ride behind and to the side of the leading vehicle, just like we would see birds doing when they fly in V formation? Kind regards, Bruce.
Hi, Bruce. Well, the answer to this is that there are really two things to consider. When you're really close to the vehicle in front, let's assume, for the purposes of this question, that we're doing this entirely safely. Let's say there's some kind of tether or a computer to make sure that no one's going to rear end anybody else, because this is dangerous and you should not do this unless it's being done as part of a proper coordinated thing. But when you're really close to the vehicle in front, because the vehicle in front of you is pushing out of the way the air that it's moving through, and that's why you have to burn fuel, because your car is doing work to move billions and billions of air molecules out of the way so the car can fit through the air. And if you've got to move a mass, even though each individual mass of an air molecule is tiny, when you add up billions and billions and billions of them, the mass is a lot. So you've got to do a lot of work to move that mass. But behind the car will therefore, or the lorry, will therefore be a void, a vacuum, an area with relatively fewer molecules in it, because they've been pushed out of the way. And because of that low pressure there, if you're right behind that vehicle in that low pressure area, your vehicle has got to push out of the way fewer air molecules than if that car or vehicle in front of you wasn't there. So, if you're doing less work, you're burning less fuel. So you will save energy by being in the slipstream of that vehicle in front of you. You see this in the Tour de France, for example, another recent event, where you've got one cyclist will sit right tucked in close behind the other cyclist. And they're doing that because the dirty air, the low pressure behind that cyclist means they're doing less work, and that means they've got more energy in reserve, and they're fatiguing their body more slowly than if they were up behind than if they were further back. A bit further back, you're not travelling through an area of zero difference. You've still got some turbulent air which is moving in the same direction as the vehicle was moving in. Because when the car goes through the air, it pushes it out of the way, but that vacuum behind pulls the air in behind the car in front, and that will create some momentum in that air. So if you drive into that, you're actually moving less air out of the way that way too, because it's already going in the direction you want to go in. So again, you're doing a bit less work. So there are two effects there that you can make use of with this. And the effect won't therefore disappear immediately after the back of the vehicle. There'll be that effect for some distance down the roadway. It will drop off the further back you are from the vehicle in front. In terms of how geese do it, you're not going to pull the same stunt unless you're a goose, because they fly in V formation, because actually the air that's tipping off the wingtips of the animal in front of and to the side of you in a V formation with flying birds, actually that's creating slightly different pressure effects because it has wings, and they're taking advantage of those pressure effects to give themselves a rest. And periodically they all swap positions so that the one who's in front doing more work actually drops down the pecking order a bit, and the ones to the side move into the front, so they help each other out by tipping air off of their wingtips and helping the one to the side of them. We don't have wings, so the aerodynamics are going to be a bit different with us, and really the effect is that vacuum behind the vehicle in front that helps us.
We often see that with marathon runners and cyclists during the course of the race. They take turns to lead a pack and conserves energy, and towards the end of the race, that's when individuals then make the breakaway.
Yeah, that's right. Because the psychology of those sorts of races is there, but the physiology of actually having enough in reserve in order to really pump for the end, that makes a big difference too. And all the time you're doing work, you are fatiguing your muscles, you're running out of energy, you're depleting your reserves, and having the oomph for that final sprint is being robbed away from you. But if you can conserve energy for longer, you're fatiguing your muscles more slowly because you're using the slipstream, you've got more in reserve, and you're more likely to be able to power past them on that home straight.
John in Tableview, I see you, but first, Gordon, Opaji, Constantia, good morning.
Good morning to you and to Chris.
Morning, Gordon.
What's your question, Gordon?
Good morning to you from a glorious Cape Town. What I want you to discuss is was pertinent about a week ago, but you had other guests on last week. The moon, our moon, describes an orbit around the Earth in a planar form. And that plane seems to be coinciding with the plane that our planets in our solar system describe. This is quite obvious in the mornings, or it was at least last week, when the moon was in the plane of the other planets that are visible in the early morning sky. I'm an early riser. And I wondered whether the intersecting planes would have an influence on the gravitational force on the Earth, and as a consequence, the tidal height. Would you care to describe the planar orbits of various things, the moon and then the solar system?
Hi, Gordon. Yes, certainly. Well, first of all, people often say, well, why do all the planets go round the sun in a flat disk anyway? Given that they've got all that space to play with, why would they all go round in the same direction along the same flat line on a plane? And this is to do with actually how the solar system formed in the first place. I'll describe that and then we can come back closer to home for the moon. The solar system formed about 5 billion years ago, and it would initially have been a big cloud of gas and dust that just by chance happened to coalesce in our cosmic neighbourhood. We think that around that time, some other nearby star probably ended its life in a catastrophic explosion, and this produced a shockwave that seemed to bump a lot of that gas and dust together enough so that gravity could take over, pull it together more tightly, and as it pulls it together more tightly, it causes it to collapse even faster in on itself, and this created the proto-sun. This proto-star would have then slowly heaped together more and more material until it got hot enough and small and dense enough to start burning. But all the time that's going on, there will be material which is still all around it in this gas pile, which hasn't yet coalesced into a disk. And because of the fact that that material is spinning and rotating, and it's spinning and rotating because everything in the universe is in motion and there's nothing to stop it. So when things come together, they add together all of their different motions and the final resulting direction of movement will be all of those different directions added and subtracted from each other, and it's the net movement that you're left with. And that happens to be a rotating sun. Our sun is spinning, and the gas around it would have been spinning in the direction the planets all orbit. And because it was spinning, for reasons of the conservation of angular momentum and gravity, the material would have slowly separated down into a disk, rather like the rings of Saturn, around that proto-star. And in that disk would have been material that had areas of higher and lower gravity, which would have pulled material together into baby planets, planetesimals, and slowly heaped more and more material together as those planets pulled more into themselves because they had a lot more gravity than the surroundings, and that gave you the planets. And because they formed out of a flat disk of material around that early star, that's why they now all orbit on that flat plane. They're also all turning in the same direction as that flat plane, with some exceptions. There are some that turn in a weird way, very, very slowly, or apparently appear to have tipped over. So we think in those cases, like Uranus, for example, which seems to go around on its side, we think that probably as the planets jostled and jockeyed with each other for position that they now have, something hit them or bumped into them or knocked them off kilter in the cases where we see funny orbits or funny rates of rotation. Now, in the case of the Moon, it's sort of similar, except that probably, and our best guess is that a big collision helped the Moon to form. So about 4.5 billion years ago, once the Earth already existed, the planets had separated out, something, probably about the size of Mars, and notionally called Theia, we think, whacked into the Earth, displaced a whole heap of material into orbit around the Earth, a bit like that cloud of gas and dust that formed our solar system in the first place. As the Earth was already spinning, as that material already had momentum and was spinning, it formed this shroud around the Earth, which slowly then coalesced into a disk around the Earth, which slowly then coalesced into the Moon around the Earth. So again, we have a Moon going round in roughly the same direction as the planet, on roughly the same orbit as the planet, on the same plane as all the other planets. And it's been doing that for about 4.57 billion years ever since.
Thanks so much for that, Opa G. Gordon in Constantia. John in Tableview, thanks for your patience. Good morning.
Morning there, Lester and Chris. I would like to know why, if at night there are a couple of ants walking around the counter and you wipe them off, and the following morning you get like 1,000 ants now have found a piece of sugar and they've suddenly swarmed all over your counter or your sink for water. How do they communicate and find their way to that either bit of sugar or a crumb or some water that has been dropped somewhere?
Is it little ant voices shouting, hey, over here?
The answer to this is that ants don't have noses. They have antennae, and that's not a joke, they do, that are very, very sensitive to smells. And they recognise each other this way. Ants produce a special unique cocktail of what we call cuticular hydrocarbons, CHBs, which are like ant BO, basically. That's how they recognise each other, so they can tell one nestmate apart from an invader. And they also lay down, as they move, pheromone trails. So they deposit on the ground every X number of steps a blob of a chemical which is unique to them and they can smell. But they put these trails down in such a way that they have a directional arrow in them. So if you can imagine walking down a path, I could just walk in a wiggly line to get where I wanted to go. But if someone else came along, they wouldn't know if I'd taken the most efficient direction to the food. They wouldn't know if I was coming or if I was going, if they just stumbled on my path. So the way the ants do it is that they put branches into their path, but the branches always come off at a certain angle when they're going away from the nest. So that this way, when the ant smells the path, it can look at the branch points and it can tell from the angle whether that's a branch point going away from the nest and therefore it follows the path towards something, or it's going towards the nest. So when ants go off foraging, the foragers leave these trails, like Hansel and Gretel going through the woods, dropping the breadcrumbs and the pebbles and so on, and they leave these branch points at a certain angle that tells any ant coming along subsequently that they can tell is from their nest that this is the direction they went in. More ants go down that path. If they stumble on whatever choice morsel that the other ants found, because they've reinforced the path on the way, more ants were more likely to stumble on that same path and follow it. And before long, you get this positive feedback loop where every ant's going down that path, finding the food until it's exhausted, and then they go off and do the same thing to recover resources back to the nest from elsewhere.
021 446 0567. That is the number to dial to ask your science and natural history related questions to Dr. Chris Smith, the naked scientist. Let's go to a quick voice note, Johannes.
Hi, Dr. Chris. Chris here as well. I was wondering why these whales that don't have any teeth don't come under attack from, say, great white sharks. How do they defend themselves if they can't bite back? Thank you.
Hello, Chris. Well, there are a couple of things to consider. Animals evolve to occupy niches in nature. And animals in one place can be very, very large, and they don't have to worry about something that predates them if that thing isn't there. So the answer is you can have some animals that live in some parts of the world where there aren't predators, because those predators don't exist in those areas. And a good example of this is if you take Australia. This country had been isolated from the rest of the world through geographical constraints for millions to billions of years. As a result, the flora and fauna there are unique and had their very own ecosystem. When Westerners went to Australia and took animals like rabbits and some to shoot and some foxes to get rid of the rabbit problem that they'd introduced, you then have a big issue because you've suddenly got, especially cats as well, and rats and other rodents that weren't natives, you've suddenly got a whole heap of animals that completely disturb and upset the apple cart because they become a predator when they weren't before. So some animals manage to exist and grow the way they do because they are so big and they occupy a niche where there isn't a predator that can exploit the fact that they have a vulnerability, because all animals will evolve to cover their vulnerability in one way or another. The other thing to consider is that everyone's frightened of something big, and so size counts. And in nature, if you become absolutely massive, then smaller animals will stay away from you because you are quite scary, because an animal of that size could quite easily mash you up, and that's not a scientific term. But nature will fight back, and in certain instances you'll find that other animals will evolve to work cooperatively so they can take on a big prey, but if they all work together. But again, it comes down to if those animals are in those areas where they could all work together to tackle a piece of prey that they wouldn't normally be able to go near if they were just on their own.
Quick question here, Chris. Why should green veggies scatter particular wavelengths of light and other veggies scatter different ones? Seems to suggest something specific about the veggies themselves. Firstly, how does, or explain the different wavelengths of certain objects?
Sure.
Chris?
When I hold up a piece of white paper, I could hold up that piece of white paper and I could say to you, Lester, this piece of white paper, and here's a piece of red paper, which has got more colour in it. And most people, I don't know if you're probably too savvy to fall for my trick, but most people would say, the red one, that's more colour. And you say, no, not right, because the white paper is reflecting every colour in the rainbow. That's why it looks white, whereas the red one is only reflecting red light. So the colour of something is that we see is because it is being illuminated with white light from the sun, and the light that's coming back to us is only that colour. And so we say this is red or this is blue because it's absorbing all the other colours, and it is reflecting, or in this person's parlance, scattering back light only of the colour that you see. So an orange carrot is reflecting back at your eye orange light, but it is absorbing all the other colours of light. A red pepper is doing the same. It's absorbing all the other colours apart from reds. The reds come back to your eye, so you call it red. And similarly, if you've got a green vegetable that's in the middle of the spectrum, all the other colours are being absorbed pretty much. The green predominantly is being reflected back, so you see a green colour. Now, we can use the colour of light that things give out to actually tell us quite a bit about the chemistry of an object. We've talked about the sun earlier in this programme. I can tell you with confidence what is in our sun. I've never been there. No scientist has ever been to the sun. So how on earth do they know what is in the sun? The answer is that because the light coming back to us actually reflects, and I mean that metaphorically, what is in the thing that it reflected from. You can read the colour of the light to work out what something's made of. This is the science of spectroscopy, and we use this in chemistry analytically all the time. So you could look at a vegetable, you could look at the colour of light coming back from it, and that will tell you something about what is in the skin of that vegetable, chemically speaking. And that in turn could be used as a proxy marker for what's in the vegetable furthermore. So really it comes down to what the chemicals there are that are in something that affect how it interacts with the light that you shine on it, and then that can tell you what that thing is. We can use this to identify vegetables actually as well.
Fascinating story which I read earlier in the week, featured here on one of our features with Bob's Wire. It says, the question says, recently a person had a successful double arm transplant. If he got his new arms from a person who was genetically predisposed to dying at 55, how does a arm or leg transplant interact with a person's genetic sequencing, Chris?
Right. Well, we could transplant anything from one person into another. So let's just ignore problems of rejection and so on for starters, and let's just focus on the idea of transplanting a body part from one person into another. Let's think about lungs, for example. People who have cystic fibrosis, which is an inherited condition, one of the most common human inherited conditions, which causes a problem with making mucus that's too sticky, so it clogs up your lungs and people develop a cough and they can get recurrent chest infections and so on. Things have got much better in recent years, and most cystics can actually do very, very well these days, but historically it's been a much bigger headache. Some people, though, can't control the condition well enough, and they do end up having to have a lung transplant. The lung transplant cures their chest problem, and the reason it cures their chest problem is you're taking a healthy set of lungs from someone who doesn't have cystic fibrosis. In other words, the genes that are running in the cells in those healthy lungs don't have the gene change that causes cystic fibrosis, so the lungs are healthy because you've got a bunch of tissue now doing the job of your lungs that come from another person, and therefore the DNA in those lungs is another person's DNA, so the recipe for the chemicals that it uses to make all the things that make the lungs work is another person's recipes, and therefore you don't have the problem. So you could say, well, does that affect the rest of my body? Well, ignoring rejection and immune suppression and that kind of thing, the answer is no. The cells in the lungs stay in the lungs, and they're that person who was your donor. And if you tested that, you would find the genetic fingerprint of your donor for the rest of your life. But if you tested the rest of your body, you'd find your own previous genetic fingerprint. So do you have a change in disease risk from the lungs that you've got? Yes, if that person had, say, an underlying genetic predisposition to develop lung cancer, for example, then you would have inherited now their risk of lung cancer because you've got their lungs. But it's not going to, for instance, increase your risk of heart disease. If they had a gene that meant they had a tendency towards developing heart disease at a young age, you've got their lungs, not their heart. So you would therefore minimally impact on your risk of developing heart disease. So really it comes down to what has been transplanted and where, but you will have parts of someone else's body running their genetic code in you for the rest of that organ's life in your body. There are other things to consider though, which is that when we do these sorts of transplants, they do often involve immunosuppression. And when we suppress the immune system, we do a range of things to the body which does change your risk of a range of other disorders, and that can have other consequences. And of course, therefore, because of you being immunosuppressed, you can be at risk of other things, and we have to watch out for those. Maybe
I watch too much true crime dramas and documentaries, Chris. But if you look at the increased use in which forensics and DNA analysis is being used in solving crimes, could we have a hypothetical situation where, let's just say, the person with the donated arm could leave two sets of DNA on a scene, the one from the donated arm and the one that's embedded in his own DNA.
You absolutely would.
Hypothetical.
Yeah. You would, yeah. Another good example of this is that if you had a bone marrow transplant, you would have a blood group that was different to the blood group you had before. So if you had your blood group documented and then you had a stem cell transplant, you could change blood groups.
Oh,
Not
wow.
everyone does, but then you would potentially have a different DNA fingerprint in your blood as well. So the answer is yes, you could do that. And if you went and committed a crime with your right hand, you could potentially leave a different genetic fingerprint than if you committed a crime with your left hand, assuming you'd had just one arm transplanted. But we are shedding tens of thousands of cells into the environment all the time. So basically you're littering the environment with bits of you, and when you walk through your house and it's dusty, that dust you can see in the sunbeams through the window in the morning, that's mostly all you and other people who live in your house. You're basically breathing in a soup of you. So the chances of being able to leave DNA just from your left hand but not your right hand is very, very slim, but not impossible.
Dr. Chris Smith, a pleasure as always, fascinating, and as always joins us again next week just after 9:30. Of course, you can go to his website, thenakedscientist.com. All of this is podcast there. Chris, have a great long weekend. Looking forward to next week.
I am very much, Lester. Thanks, everyone. Have a lovely weekend. See you next time.